Hello everyone. I would like to welcome you all to this webinar on modeling elastic plastic analysis using MSC Nastran. My name is Vijay Tunga. I work as a senior application engineer. I work out of the Ann Arbor office based in Michigan, in the United States. As part of the webinar today, the agenda, this is the agenda for the webinar today. We'll kind of have an overview of MSC Nastran, and we will look into some of the nonlinear material models available in Nastran. Our primary focus will be in the area of elastoplastic material. We'll be covering a few important basic concepts in modeling elastoplastic material. In the end, we'll have like a small demo using Patran on how to model elastoplastic material inside Nastran, and I'll conclude with the summary slide. So the first one is, let us kind of take a look at an overview of Nastran. MSC Nastran is a leading CAE solution offered by MSC Software. It was introduced in the early 60s. It has an extensive solution procedure in terms of solving problems involving like linear statics, linear dynamics, nonlinear statics and nonlinear dynamics, acoustics and optimization. In the past maybe 5 years to 6 years, there has been heavy focus on integrating all these different solutions into one CAE environment in the form of analysis chaining that you see on the right hand side. This could be, for example, doing like a thermal analysis followed by a structural analysis, or it could be like a nonlinear static analysis followed by a nonlinear transient analysis, or it could be a co-stimulation of a thermal mechanical structural analysis. So that is what we call as the coupling analysis. So MSC Nastran is the industry standard solution, and it's with an open input file format, and it is adapted and supported by several preprocessors in the industry today. And we talked about the different analysis capability of Nastran in the previous slide, including all the way from static analysis to optimization, superelement, and parallelization. It has superior scalability and accuracy in terms of parallel processing. It has both distributed memory in parallel and SMP. SMB capability as part of the solution. So that is kind of like a high-level overview of Nastran functionality and the solution procedure available inside Nastran. Next one is to understand or review the nonlinear materials available inside Nastran. Let us look at some of the sample applications that Nastran is used today in different industries, for example, the automotive, aerospace, and heavy machinery. And any component that involves like metals or thermoplastics involves material modeling in terms of using the elastoplastic material definition. And there are certain other applications where Nastran is used today and nonlinear materials of Nastran is used today. For example, if you look at the last one under the automotive, the seals, the boots, and the bushing requires the elastomeric material formulation inside Nastran. And if we look at the airframe under the aerospace, it requires the use of composite materials and progressive failure analysis for these composite analysis. And also, if you look at the heavy machinery, some of the applications include like crack propagation and delamination in terms of modeling the virtual crack closure techniques and cohesive zone modeling and so forth. These are all part of material modeling, nonlinear material modeling inside Nastran. Here are other applications of how Nastran is used today in the area of like consumer goods, electronics, biomedical, and oil and gas. It is important to note, for example, the electronic portion where the thermal material modeling is required inside Nastran. And if you look at like the oil and gas application, the packers, it requires the modeling of materials in terms of the elastomers, elastomeric representation of the material models, and also the gaskets. So all these nonlinear materials are available inside Nastran, and it includes the basic elastoplastic material model, which we will be focusing today. It also has like a nonlinear elastic material. The elastomers, we talked about some of the application in terms of the packers, the seals, the boots, and so forth. And we talked about the composites used in the aerospace industry and progressive failure analysis related to composite modeling. And there are certain applications which include the engine block, the cylinder, and the gasket material in between them. These materials are also available inside Nastran. And I briefly mentioned about VCCT and cohesive zone modeling. Those are part of the crack material failure models available inside Nastran. And finally, the creep material and the shape memory alloy is also available inside Nastran. The shape memory alloy, for example, is used heavily in the medical industry. The image that you see at the bottom is a stent analysis, and it uses the shape memory alloy material formulation inside Nastran. Here is an animation of like an elastomeric material model that is available inside Nastran. Having said that, we have quite a bit of nonlinear material formulation. Our focus today will be on the elastoplastic material available inside Nastran. And the demonstration that we will be going through is a sheet metal forming application that you see in the image. So when we talk about the elastoplastic material formulation, the first thing that comes to our mind is like a uniaxial tensile test and the stress strain curve that we derive from the uniaxial tensile test. And the stress strain curve kind of has like the linear and the nonlinear stress strain relationship. The linear response, so there are a couple of important items to derive from this stress strain curve. The first one is the linear portion. So for example, the sigma y is the yield strength of the material, which characterizes the linear elastic portion of the material, which means at any point in this stress strain curve, upon unloading, will go back to its original position. Any point in the stress strain curve after the yield strength is in the plastic or the nonlinear portion of the stress strain curve, which upon unloading, say for example, when we unload the material at point 2, it follows the line that you see here with the slope of the Young's modulus of the material, and it has like a permanent set. Here you can see with the plastic strain 2. It also has an elastic component. For example, the total strain at point 2 has like an elastic component and the plastic component, and the elastic component is responsible for the spring back in certain applications like metal forming and so forth. And the same applies to point 3. So when the material is unloaded at point 3, it follows the dotted lines that you see here with the slope of the Young's modulus, and the total strain at point 3, which is the point here, is comprises of like the elastic portion, which is the spring back, and also the permanent plastic deformation of the material, which you see here. Okay. So in while simulating this stress strain curve, there are several simplifications or different formulations, or I can call different varieties of stress strain curve that we use in our analysis today. I would say the simplest form is the elastic perfectly plastic, which basically requires the Young's modulus and the yield strength of the material. The piecewise linear is the stress strain curve that we talked in the previous slide, and also the bilinear is where we specify the Young's modulus and the hardening slope of the material to capture the plastic portion or the work hardening or the strain hardening portion of the material. And there are like other simplifications where the materials can undergo like rigidly plastic material formulation. When talking about plasticity model, three important things come to our mind. First one is the yield criteria. We talked about the stress strain curve that we obtained from the uniaxial tensile test, but in reality, the structures undergo like multi-axial loading, and to have and we have to come up with like an equivalent stress from the multi-axial loading and compare it with the yield strength of the material to define the onset of the plastic deformation in the material. And there are several yield criteria or yield condition available inside, including von Mises, Hill, Bartlett, Moore, Coulomb, and so forth. The one that we will be focusing today and the most commonly used yield condition or criteria used in the industry is the von Mises criteria. The second thing is the flow rule for plastic deformation. It kind of describes the differential change in the plastic components, strain components, and it's a function of the current stress state. Basically, it gives the magnitude and direction of plastic strain. We have an associative rule inside Nastran, which primarily tells that the vector of the plastic strain is normal to the yield surface that we obtain from the yield criteria above. And the final thing that comes to our mind in terms of plasticity modeling is the hardening rule, and there are several types of hardening rule, including like isotropic, kinematic, combined, and so forth. Again, the most commonly used hardening rule or the work hardening portion rule is by defining using the isotropic hardening rule. And again, there are other different flavors of plasticity in terms of you can have like a stress strain curve as a function of temperature that you see in the graph, like as a T1 and T2. The Young's modulus can change with respect to temperatures. The work hardening portion of the curve can change as a function of temperature, or the stress can change as a function of strain rate, as you see in the next plot here. So we talked about the yield condition or the yield criteria. Again, this is needed because in reality the structures undergo multi-axial loading, and to compare it with the yield strength of the material obtained from uniaxial tensile test, we have to use the stress components, and there are several criteria that we saw in the previous slide, and the von Mises criteria, stress criteria, comes up with the equivalent stress based on the equation that you see here. In the 2D principal stress plane, the yield surface, so we define the yield surface is an ellipse. In the deviatoric plane, the yield surface is a circle. So any stress state inside the yield surface is an elastic region, and any stress state on the curve determines the onset of the plastic portion of the material. And this is the stress criteria again we'll be using during the demonstration today. The next one is on the hardening, isotropic hardening. So basically, when we look at this curve, the point 1 is where the yielding starts for the material, and the point 2 to 3 is where the hardening happens. From 1 to 2, the hardening happens, and then there is an elastic unloading. And then 3 to 4 is again the elastic loading followed by the new hardening. And the yield stress now becomes from point 1, it has increased in size to this point 4, to this location, the point 4. And basically, isotropic hardening tells us at this point, when we release the load and kind of compress the material uniaxially in the compression direction, the yield stress at this point, at point 5, is equal to the stress obtained at point 4, and from there on, further loading causes the stress to increase from there on. Basically, if you look at the yield surface in the deviatoric plane, we are saying that the yield surface increases in size radially outwards as part of the isotropic hardening. Okay. So some of the common terminologies that we come across when modeling stress-strain curve is like the engineering stress and the engineering strain curve. Basically, the engineering stress and the strain are computed based on undeformed shape dimensions as a reference values, which means the area that we use, the force divided by area that we use is the undeformed or the initial area. And the engineering nominal strain, engineering or the nominal strain is given by L minus L0 divided by the L0, where L is the new length and the L0 is the original length to derive the nominal or the engineering strain. Most of the time from the lab, when we get the stress strain curve, it is in the form of like engineering stress and the engineering strain. However, it is important to understand how Nastran solves the stress strain behind the scene. And basically, Nastran uses true stress and true strain to account for changes in the area during the deformation, which results in more accurate mathematical model. So the question is, how do we go from engineering stress to engineering stress strain curve to true stress true strain curve? Again, these are the equations that we use for the true strain. It is a natural log of the new length divided by the original length, and the L stands for the instantaneous length again. And here, while computing the true stress, the area is the new area or the instantaneous area that happens during the deformation, as opposed to the initial area that was used in the previous slide while computing the engineering stress. There are two options available inside Nastran for the user to model the material. The user can either model the true stress and the plastic strain portion of the stress strain curve, or he could use the true stress and the total strain curve inside Patran, and Patran will automatically set the fields accordingly using the table S1 cards. So the important thing that comes to our, as part of our discussion is, now we have defined what is the engineering stress, engineering strain curve, and I already told you that Nastran and typically any finite element solver uses stress strain, true stress and true strain. So we have like some basic equations that you see here to convert the engineering stress to true stress and engineering strain to the true strain. Once we compute the total true strain, we can remove the elastic portion from the total strain to compute only the plastic portion. So as I mentioned in the previous slide, the curves that you see here uses the plastic strain, as you can see, this column as the x-axis and the true stress as the y-axis. So this is one format in which Nastran can take the stress strain curve. And the other format is the true stress and the total true strain, and Patran can change the fields accordingly, and you could use that one as well. But for the demo, we will be using the true stress and the true plastic strain as part of the demonstration today. So let us kind of look at a simple example. Here in this case, it is a sheet metal forming example, and the sheet metal itself is modeled using the elastic plastic material available inside Nastran. And of course, we'll be modeling the sheet or the elements as a deformable body, and the punch and the die as a rigid contact body inside Nastran. Again, the goal is to have the punch move down by 28.5 millimeters and have the metal forming and look at the metal forming simulation. You can see here on the right hand side the original position of the punch and the final position of the punch when it does the metal forming process. So at this time, I will go into Patran and kind of show you how We can use the materials that we talked about in terms of using the stress strain curve. Again, the requirement is to have the true stress and the true plastic strain curve to be input into Patran. Okay. At this time, I will go into Patran, and I have brought in the geometry of the punch and the die inside Patran. For those who are not familiar with Patran, is the preprocessor and post-processor for MSC Nastran solver, and also it is the pre and post for several other solvers like Ditran, Mark, and so forth. So what I have here is on the left-hand side is three groups: one for the die, one for the punch, and one for the workpiece. The workpiece again is modeled as 500 elements, and the die and punch will be modeled as rigid contact bodies inside Nastran. So the first thing that we will do is to go into the fields tab here and create or import a stress strain curve inside Patran. So I'll go into create material property and provide a name, stress strain. Let's give a simple name here, and then we'll activate the strain. And in the input data, we'll go ahead and import the CSV file, which contains the true stress and the true plastic strain. And we'll say OK. We'll say apply. And now we can go ahead and see how it looks. So we'll go to show the stress strain curve, and we'll use the existing points that were specified in the stress strain curve. And we'll say apply. So this is the stress strain curve that was available in the form of CSV file that we could import into a Patran. And here are the plastic strain portion and the true stress portion of the stress strain curve. Again, the most important thing to note here is the yield stress of the material is the first point that you see here. In this case, it happens to be 194 Newton per millimeter square. Okay. So once we define the material, we can go into creating the properties of the metal workpiece here. So we'll go ahead and create like a shell element property, and we'll be using the thick shells to take the transfer shear strain into account. And we'll select the material. Okay, the most important thing, I forgot to show you that one. Okay, the most important thing is to create the materials. We'll create this elastoplastic material. The first one is to specify the Young's modulus. In this case, we'll be using 70,500 Newton per millimeter square, and the Poisson's ratio. Since we are using a nonlinear static analysis, the density doesn't matter. We'll put at 1, we'll say OK, and we'll say apply. And the next one is to define the plastic portion, and again we click on the input properties. We change the constitutive model from linear elastic to elastoplastic, and at this time Patran can take in the stress strain curve that we defined. And again, there are several forms of stress strain curve that I described in the presentation, and we'll be using the piecewise linear stress strain curve, right? We'll be using the von Mises criteria. We'll be using the isotropic hardening that we talked about, and we'll be selecting the stress strain curve that we imported through the CSV file into Patran. We'll say apply. And now I can go into properties and use the thick shell element formulation and create the properties here by selecting the materials and elastoplastic material, and specify thickness of 1 mm for this sheet metal. Say OK, and go ahead and select all the elements on the screen. Say add, OK, and apply. So at this time, we are pretty much ready to do the analysis, and the only requirement here is to define the contact bodies. So I'll go into loads and boundary condition, create contact. First, we'll create the deformable body for the workpiece. So I'll call workpiece. This is the 2D element. So I'll say select application region, find elements. I'll select all the elements of the workpiece as one contact body. You say add, OK, and apply. And the next step is to define the rigid, use the rigid surfaces as it is, and use them as rigid contact bodies inside Nastran. And to do that, we'll be creating, using the option, we'll change it to the rigid body. And first let us define the one for the punch. And at this time, we can, using the input data, we can move the rigid body by several methods. One is the velocity, position, or the force. I'm going to use the velocity method and kind of move the punch by 28.5 mm. In this case, our total time is 1, so my velocity is 28.5. And we'll just say OK and select application region. I'll select the punch surface in green. Say add, OK, and apply. And finally, we'll create one for the die, and again it is a velocity based, but the die is going to be fixed in space, so I'm not going to move it in any direction. So I'm going to say 0 velocity in X, Y, and Z. I'm going to say OK and select application region. I'm going to select, maybe I can turn off the die and the punch and the workpiece and have the die, and select all the surfaces of the die. Say add, OK, and apply. At this time, we are pretty much ready to write out the input file. So let us bring back the punch and the workpiece, and we'll go to analysis. And we are ready to write out the input file. We'll select the nonlinear solution sequence inside Nastran. And there are several options available in terms of selecting the friction model and so forth. I will just say apply. Let's call it demo 1 and we'll say apply. So at this time I finished writing out the input file. In the interest of time, I'll be not running. I will not run it right now, but I have run this solution already, and I'll bring up another pattern session where I imported the results of this simulation. And basically, you can see the workpiece, the punch, and the die. And you can see the simulation time is 1. So the velocity of 28.5 will move the punch 28.5 millimeters down, right? And we'll look at the nonlinear stresses and the displacement. We'll click on apply. And this is what we had set up in the previous session of pattern. Okay. At this time, you can come and query the stresses and strain and kind of see if Nastran is following the stress strain curve that you defined through the CSV file by outputting the stresses and strains, and you can backtrack and overlay it on the CSV file's stress strain curve and see if Nastran is following it exactly the way you defined. Okay. At this time, that concludes my demo. I'll go back into my presentation. And I put in like a summary slide just to kind of give a high-level summary of what we discussed today in terms of the different types of material model, a nonlinear material model, I should say, in Nastran. We talked about briefly about them. And we spent quite a bit of time, not a whole lot, but the basic concept of the elastoplastic materials in terms of the von Mises yield condition, isotropic hardening rules. And there are, we briefly mentioned about the temperature-dependent stress strain curve that we can specify, and also the yield stress as a function of strain rate can also be specified. During the demo, I mentioned about the contact capabilities available in the nonlinear solution sequence in Nastran, both deformable bodies and rigid bodies for the die and punch. And finally, to do like a nonlinear simulation with nonlinear materials, we need to have nonlinear elements to capture the plastic strains. We are talking about plastic strain greater than 5%, and we need like nonlinear element formulation inside Nastran, which is also available as part of the nonlinear solution sequence. That kind of concludes my presentation today, and I will transfer the control back to Srinivas at this time. Thank you.
Yeah, thank you very much, Vijay.